questions? Any comments, questions as we continue? Okay. So I'm going to consider one more topic when it comes to binary phase equilibria. We constructed the phase diagram over the last few lectures for systems that have two components, chemical components, and two phases. And the two phases are liquid and vapor. And we considered the case where both of the phases are ideal. And I discussed what it meant to be an ideal vapor or ideal gas. And that's something you already know. And for an ideal solution where you have the condensed phase, I discussed that really ideality means a renormalization, if you want. And by renormalization, what I mean is that everything is equal now. It's normalized such that all interactions are the same, regardless of whether you have two different types of chemical species. The interactions between everything in your system are the same. It doesn't matter what your label is, right? And so some systems, real systems approximate this, and you've heard this before, like attracts like. So, you know, nonpolar liquids can form ideal solutions. Polar liquids can be mixed to form ideal solutions. And so in the condensed phase, ideality means equality of interactions. And again, this is an assumption, but it's a starting point. Just as the ideal gas is a starting point for something, otherwise we couldn't get anywhere. Okay, so we constructed the phase diagram last class in full for a binary system, and here is the phase diagram that we ended with. And it's really at a specified temperature, okay, because that's one of the degrees of freedom that we chose to use. And so that leaves us with 1 degree of freedom in this case. And so that could be pressure or composition. And so depending on what we choose, we need to have a way to figure out what the remaining variables in the system are once we specify the 2 independent variables. And so in that case, knowing what pressure, total pressure and composition of both phases gives you the phase diagram, again, at the specified temperature. And what we found is that the total pressure is related to the liquid phase composition given as a straight line. So that would be this guy. Yeah, so this is the straight line, and I won't draw the whole thing, but this is the straight line. That gives you total pressure in your system as a function of the composition of the liquid. Okay, and I don't want to mess up the plot here. And then the variation of the total pressure in the system with the vapor composition is given by that purple or magenta curve, which is a curve. It has curvature, and that's really because the dependence of P total on Y, the vapor phase compositions, is not linear. It's 1 over Y dependence, and so you have some curvature to that. Okay. The other thing to note here is that we've picked species A and B, and this is very general. And in this case, at this endpoint in this plot, we have all A, and at this point, we have 0A. And since at this temperature, the total pressure in the system at the endpoints really is just reflecting the vapor pressures of the individual species, right? At the endpoints, you have either all of one or all of nothing, or all of the other. We see that when we have all X, all A, we have a higher total pressure than when we have all B. What that means is A is more volatile. A is more volatile than B at this temperature. And volatility just means the propensity of molecules of a particular chemical species to escape into the vapor phase. And this is really a reflection of the interactions, right? AA interactions must not be as strong as BB interactions Otherwise, at the same temperature, um, we might have the volatilities may be flipped. The other thing to remember is that perhaps A is heavier than, A is lighter. If A is lighter, then at a particular temperature, it would be more volatile. Okay, more of its particles can escape into the vapor phase. And as we'll see next semester in 444, systems at the same temperature is related to kinetic energy, which is the motion of particles. And it turns out that at the same temperature, if you have a light particle and a heavy particle, they'll have the same kinetic energy, but they have different masses, right? And so that's going to affect how things play out in terms of many different properties of systems. And in this case, one can say that a heavier particle would be less volatile than a lighter particle. Okay, but in essence, that's a detail. At the more gross level, to see the forest here, we say that A is more volatile than B because it has the higher vapor pressure at this temperature. Okay, and we saw then that once we have our two-phase diagram, okay, here is P total, here's X sub A and Y sub A, that goes from 0 to 1, and we can just redraw this again. Okay, this was the all liquid region, this was the all vapor. Okay, we still have mixtures. Okay. And in between, this is the two-phase region right here. Okay, so that's the two-phase. Region of our phase diagram. And so if you have any combination of pressure and composition at this temperature, any point that resides in this area that has the red slanted lines is going to have two phases in coexistence equilibrium. All right, any questions or comments? Any need for clarification? Because I want to go into now addressing the question of, well, okay, the system, the phase diagram tells you something about composition and pressure and temperature, but it really doesn't tell you about what might happen if you start with a certain amount of, let's say, liquid. Okay, so let's say you start with a certain amount of liquid. I'm going to keep redrawing these things. Okay. And so let's say you start with a point here where you have all liquid. Okay, so that's going to be, I'm just going to drop a line down. So actually, let me move these guys. So this will be X of A superscript naught. So that's your original point. So you're in the all liquid region, but the composition of liquid is going to be X of A naught. Okay? And let's say we have at this point N total. Okay, so N total is equal to the number of moles we have of liquid initially. Okay, so we have some amount, and that's something that's, you know, we would know how much we have if we're going to start at some point. Okay, so you can easily tell how many moles of liquid you have. And now what we're going to do is reduce the pressure. So we're going to reduce the pressure until we get into the two-phase region. And we know that the two-phase region is this region right here. So we're going to find some pressure. We'll just pick a pressure in the two-phase region. Okay, and let's just do that. So we're gonna keep we're not gonna move laterally, we'll just go vertically down. We're just gonna reduce the pressure. And so we can maybe get to this point right here. Okay. So we've reduced the pressure to a value that corresponds to the y-axis of that point, that red point in the two-phase region. So that's our pressure now, total pressure. Okay. And since we know that this is the two-phase coexistence region, we have to draw these things called tie lines. They tie together the two phases. And so the tie line for this system, well, we can get the liquid phase composition by moving towards the curve that gives us all of the compositions of the liquid, and that's the solid, that straight line. So we just kind of move in this direction, and this will give us the composition of the liquid, okay, at that pressure. And then the composition of the vapor will be given by moving in this direction here, okay. All right, so now we know at that pressure that we ended up, starting with all liquid, okay. So we started with all liquid. Good. And then we reduced the pressure at constant temperature. Okay. And then we get to a point, in this case, we're just going to stop at a pressure where we have two phases in equilibrium. Okay. And so we have two phases in equilibrium, and we know their compositions. Okay. So we know the liquid and vapor phase compositions. Okay. So we know that because we have the phase diagram right here. So that's not an issue. So the question then, okay, we start with all liquid and we say that we have N total moles. Okay. So the question is how many moles of liquid and vapor do we have? Okay, so we started with N total moles of liquid, okay? And once this thing splits, once our system splits into a liquid and a vapor phase at this coexistence pressure, we may want to know how much of this is going to be in the vapor phase and how much of this is going to be in the liquid phase. Then again, if you're thinking about this in terms of separations, we see that if A is the species you're interested in, the vapor is going to be enriched in A, just looking at the phase diagram here and where we stopped in this two-phase region, right? Compared to where we started, XA naught, the composition of the vapor is going to be higher. Okay, and that's given by this point. Okay, so that's YA at equilibrium, right? When we have this two-phase coexistence, it's much higher than XA naught, the composition that we started with in our N total moles of liquid. So we want to know how much vapor we're going to get, perhaps, because that way we'll know how much A we have at the end of the day, if that's the chemical that we're interested in. So the question then is, how many moles of liquid and vapor do we have at equilibrium? And so to do this, we're going to do a mole balance. And so the answer then, mole balance on A. We could do B too, but we're dealing with A. So mole balance on species A. Okay, and once we do this, we'll get the answer. Okay, so let's start the analysis. It's very simple. Okay, so here's the analysis. So we're starting with N total, right? So our moles of A, which is a constant, Okay, because in this case, we haven't said anything about chemical reaction. So the number of moles of A has to be a constant. Okay, so initially we had XA naught times N total. This was our initial and constant number of moles of A. Okay, so this is equal to the constant number of moles of A. Okay, our initial composition was XA naught. Okay, and we had N total moles of liquid. So it's simple. That's what we have as the moles of A. Once we have the split, okay, into a liquid and vapor phase, we're going to have A in the liquid and we're going to have A in the vapor. So the moles of A in the liquid which I'm going to call L, is just going to be X of A, which is the mole fraction of A in the liquid, times the moles of liquid. So N sub L is equal to the number of moles of liquid. Okay, and then moles of A in vapor, V is equal to Y sub A times N sub B, where N sub B is equal to the number of moles of vapor. Okay. So once we had this split of that originally all liquid system into a liquid and a vapor phase, the moles of A in the liquid and the moles of A in the vapor, when you add them up, are going to have to equal the original moles of A that we had. The original moles that we had are this guy. This is the moles in the liquid, and this is the moles in the vapor. So we have this relationship, X sub A naught is equal to N total. X sub A times N total is equal to X sub A in the liquid times the moles of liquid plus Y sub A times the moles of vapor. Okay. Now in this case, this is known. Okay, check mark. X sub A is known. Y sub A is known. Our unknowns are N sub L and N sub V. And why are XA and YA known? Well, we just discussed that. This is Y sub A at the split, liquid vapor split. And this is X sub A at the vapor liquid split. Okay, so those are known from the graph, from our phase diagram. And we know X sub A naught, that's what we had initially. Okay. So everything is known. And in fact, N total is known too. We knew how many total moles we had initially, all in the liquid phase. And to get at what this number of NL and NV is, or really the ratio, all we need to remember is that N total, the total number of moles, is going to have to equal NL plus NV. Remember, we started with all liquid, but once we have that all liquid system splitting, again, the total number of moles cannot change in this system. We're not creating matter and we're not destroying matter. Okay, there's no chemical reaction at the moment. And even if there were, at the resolution that we want to discuss it, we would have to have the total number of moles of various atoms conserved. So this relationship in this case is easy because we're not having any chemical reactions. So the total number of moles, A plus B, is going to be the total of A plus B in both the liquid and the vapor phase. Does that make sense? Okay. So that's why we can write this equality here, which is not too profound. It's rather obvious. So what we're going to do then is stick this guy into this equation. So we have XA naught times N liquid plus N vapor is equal to XA times N liquid plus YA times N vapor. Okay. Now we're just going to do some algebra, and what we want to do is collect all of the N sub L terms and the N sub V terms so that we can see what we can manage this a little bit because they're all split. So I'll bring all of the N sub L terms to the left-hand side. So I'll have N sub L times XA naught, and then this term will come over to the left. So that'll give me N sub L times XA, and then we'll have all the NV terms on the other side. So I'll have NV times YA minus NV times XA naught. Okay, that's just simple algebra. So on the left-hand side, we have N sub L times XA naught minus XA. Remember, XA naught is the original liquid phase composition where we had all liquid, and X sub A is the composition of A in the liquid when we had that split into two phases. And on this side, we have n sub v times ya minus xa naught. Okay. Again, it's ya is the vapor phase composition at equilibrium, and x sub a naught is what we started with in terms of composition. And so now we can choose to either get n sub L over n sub V, or it doesn't really matter, n sub V over n sub L. We can divide either side by one of the n's. So we can get a ratio of the moles of liquid to vapor. Okay, that's what this allows us to do. Again, this is known from the phase diagram, this is known from the phase diagram, and this is known as the initial composition. So we just solve for the ratio, and I'll just solve for NL over NV. So NL over NV is equal to, let's see, what do we do? YA minus XA naught divided by XA naught minus X of A. So this tells us the ratio of moles of liquid to moles of vapor. Okay, and this is very, very nice and very neat. Okay, that's the ratio we have. And so this might be, it could be 0.3, it could be 0.5, it could be 0.9, right? If it's 0.9, we know that 90% of the original liquid still remains as liquid. If it's 0.1, then that means 10% of the original in total moles. So once we have NL over NV, which is just some fraction, right? So, and this is known. So these guys are known. All of these guys are known. You can read them from the phase diagram, which means that this ratio, we can call this F for fraction, let's say, right? This ratio or this fraction is known. Okay. Any questions so far? So we know what that is. Okay. So what does this mean? Well, if you look at this geometrically, what this is saying is that the ratio of liquid to vapor, right, is given by this ratio. So what is YA minus XA naught? Well, YA minus XA naught is this distance right here. That's YA minus XA naught. That's that distance. And then XA naught minus XA, which is on the denominator, XA naught minus XA, is this distance. Okay. So what we find is that the ratio of liquid to vapor is given by these distances on the phase diagram once we know where we are, what pressure and what compositions for the individual phases. And it turns out that the liquid to vapor ratio is just this length divided by this length. Okay, any questions? And that's in this thing, any questions so far? Geometrically, that's all that is. So in fact, if you were to be given a graph or a phase diagram and the composition of the two phases, you should be able to tell the ratio of liquid to vapor in the system. It's just geometric. Okay? And that geometry really is just these two lines. Okay, so this is a line segment and this is a line segment. And this is called the lever rule. Okay, again, this idea of rule, but it's just something that comes out from a mole balance. It's really a mole balance, a mass balance. So it's not really any profound or magical rule. It really is just a balance on mass.
They call it a rule because it has to do with torque, or it's similar to torque.
Well, it's called that because of it's called that because of lever. Yeah, it's called lever because of that. That's correct. That's correct, Sheldon. So really, it's if you look at let's say a seesaw, and you have, remember from physics, a fulcrum where you can now have, let's say, how do we want to do this? This thing is going to teeter-totter, right? So if your fulcrum is there, where would you have to put the heavier mass to have this thing be equal?
On the left-hand side.
Okay, yeah, let's say we have two masses. So here's mass 1, and then the smaller mass would be here. So let's say M1, M2, M1 is greater than, M2. Right, and so this is the same thing as what we're finding here. So in this case, the length from the fulcrum to the end here, right, is much larger than the length from the fulcrum to this side. Right, so it turns out then that this length, the ratio of this length to this length, is really going to give us a ratio of M1 to M2. So if I let this be L1 and I let this be L2, actually this is the length from the fulcrum to mass 2. This is the length from fulcrum to mass 1. This is going to be L2 over L1. Okay, and this is why it's called lever. So forget about this is why it's called lever. Okay. Yeah, and you're right. You're generating torque and you're balancing torques, which is exactly right. Which is a force times distance. Right. So did I answer your question, or at least address that sufficiently?
Yeah. Thank you.
Okay. Thank you. That was a good point. So you remember your physics. Good. Very good. We'll be coming back to torques and angular momentum next semester when we do quantum mechanics. So, I encourage and invite people just to refresh your memory about angular momentum, because that's going to be a large part of quantum mechanics, right? We know that orbitals and we know about angular momentum and stuff like that. So it's very cool stuff. Okay, so that's the lever rule. Okay. Any questions? Maybe a bit too drawn out, but it's okay. All right. So one thing I want to now address, okay, is the chemical potential of the liquid. Okay. Any other questions on that? Okay. So back to chemical potential. Okay. So here we have our vapor, here we have our liquid, we have our AB, okay? So, and it's ideal, and ideal. We know at a particular temperature, and let's say we also know the pressure, right? I mean, the system is going to be in equilibrium. We know that mu A in the liquid at this temperature is going to equal mu A in the vapor at this temperature. And this is something that's very profound. This is something that one must take away from this course. Okay, this is the starting point for many things, including even chemical equilibria, once we understand a little bit more of what's going on with thermodynamics. So we have this very important relationship, and it's just totally from thermodynamics. Sorry?
I don't know if you're writing, but for some reason can't really see if you're writing. Kind of hear like a pen moving on a surface, but can't really see anything.
Oh, when did this stop?
All right, here, I can see it now.
Okay. 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 Yeah, thanks for chiming in if there are problems. It's very important. Let me just, okay. Where was I? Okay, right. So we know what because of this, well, we figured this out. Remember a couple of lectures ago, I kind of reminded everyone what mu A vapor is for an ideal vapor or an ideal gas. Remember? And so I wanted to recall or make people aware of that again, because we can use that result to get this. Okay, we can get the solution phase, because remember, the ideal gas is very simple. There's no interactions, and we have all of this mathematical and physical models and formulations for the ideal vapor and ideal gas. And so this allows us to extend and apply those things to the liquid, where now the liquid phase is actually one of these phases that's very, very, it's a strange being. The solid is one thing, right? Where you have order, crystals, there's in very short range order. Vapor is where you have very long range correlation. Uh, sorry, the solid is where you have very long range order and correlation. In the gas, you have very, very, very short range correlation, right? A gas molecule, really, they're so far apart relative to a solid that there's no correlation except on a very long scale. But this liquid is like really a strange beast. It's a fly in the ointment. And so in this case, we can use our development of the vapor phase, the gas phase, to attack the chemical potential of the liquid. Okay, and this is going to lead us to an insight that we're going to use for non-ideal systems. So let's recall that mu A vapor. So we know that mu A liquid is going to equal that of the vapor, okay, at this temperature and pressure, of course, and composition, because we know that chemical potentials G are dependent on composition. So mu A vapor at T, let me just remind you, is going to be mu A at some reference pressure, okay, that we choose at this temperature. So that's what this means. The chemical potential A at some reference pressure at this temperature plus RT natural log partial pressure of A divided by that reference pressure. And of course, we need to have that reference pressure there because obviously log, the argument of a log is unitless, and obviously it comes out that way when we do the math. So go back and look at your notes and in the text as well, you'll see that that has to be there. The only reason you don't see it is because it's often taken to be 1 bar or 1 atmosphere, PA0, superscript 0. Okay, so that's great. And let me just remind you that this mu A vapor is equal to mu A in the liquid. Okay. But this is great. Remember what we said about the ideal solution. We said that PA, the partial pressure of A, is related to X of A times PA vapor, the vapor pressure of A. Remember, this was Raoult's law. Again, one of these, it's really just a model. Okay. So it's just a model of how the vapor pressure of species A above a liquid vapor system is going to be related to the mole fraction in the liquid. Okay, not in the vapor, but in the liquid. So this was our convention. So we can put this guy in here. So we have mu A in the liquid phase at this temperature is equal to mu A at this temperature at some reference pressure plus RT natural log X of A times PA vapor pressure all over PA naught. Okay. Any questions? That's actually rather simple. And then we can just carry everything. Now the math is very, very simple. This is just mu A at that reference pressure. Now we're just going to split what's in the log, because remember, the log of a product can be written as the sum of the logs. So here we're going to write RT natural log PA sat, which is the vapor pressure of A at this temperature, over PA naught, plus RT natural log X of A, where X of A is the composition of A in the liquid. Okay. And what we see then is mu A in the liquid is equal to mu A naught T plus RT natural log PA vapor over PA plus RT natural log X of A. But this guy, okay, is just mu A at the saturation pressure at that temperature. Remember, if you start with mu A, so when we think about the chemical potential of a particular species, there's always going to be this sequence, right? There's going to be a reference state chemical potential plus anything that takes your system from that reference state to whatever other state it is, okay? And so these first two terms on this last equation that I wrote represent starting at a reference state. So we have this superscript 0 defining some reference state. And then we're going to add the change to go from the reference state to another state. And in this case, that state is pure A at its liquid vapor equilibrium point, but now it's pure A. It's just pure A, right? Because all I have in this log is the ratio of the vapor pressure of A at this temperature over that reference state pressure, okay? That's why I can lump that together and just say, well, that's the chemical potential of A at its saturation point, or the point where we have pure A in equilibrium with liquid and vapor. Okay, it's liquid and vapor are in equilibrium. So that's what that first term represents. That's all it is. And then all we have is this residual. So that can be taken as a reference state now. That can be taken as a different reference state. The reference state now is just pure A, where you have A and it's liquid and vapor in coexistence. That's all that means. It's a matter of interpretation, and that's how we're going to interpret it. It's fine. So this becomes mu A, the chemical potential of A at the temperature of interest, where we now have A in liquid vapor coexistence. And so this sat is the saturation, or again, it just means at that vapor pressure point. Okay. Right? And then we have the extra term RT natural log X of A. It's not extra, it's actually necessary. It has to be there. And that represents now the contribution to the chemical potential of A because of the liquid, being in the liquid. And so for an ideal solution, where we say solution is a liquid, okay, this is the chemical potential of species A in an ideal solution. So this means liquid, or really condensed phase. Okay, and that's a fancy physics word for meaning liquid. Okay, although they apply condensed phase to solids, but it's okay. All right. So here, what we see, if we go back to this expression, is the same theme that we saw for the vapor. Okay, what we see here is that the chemical potential of a species A in the liquid at a particular temperature and pressure is going to be the chemical potential of that species in its pure form. Okay, but that pure form corresponds to the equilibrium of liquid and vapor, okay, at that temperature, whatever that pressure may be at that temperature. Okay, so that's what that means. Plus the contribution RT log XA. And since XA is going to be anywhere from 0 to 1, and of course, if you have a mixture, we don't count 0 and 1, it's going to be something that's a fraction. So the log of a fractional number is going to be negative. So that term that's at the very end of this equation reduces the chemical potential of A, or any species in an ideal solution. It reduces the chemical potential of that species in the solution relative to what it would be if it were pure. Okay, so we have a solution, okay, of many components. It's a solution, it's ideal, it's in equilibrium with the vapor. Okay, so for the binary system, you can have A and B. A can be in both phases, liquid and vapor, okay, in that mixture, right? If we take the reference state as A, having its liquid vapor coexistence state, okay, but no B, just pure A, the fact of being in this mixture now leads to a lowering of the chemical potential of A. And as you see from our, if you remember from our discussion of delta S, okay, when we had mixtures in an ideal vapor, we had things that were RT log Xi or Xi log Xi. And so in this case, not RT, for entropy, you don't have the T, it's just Xi log Xi. This is reminiscent of an entropic contribution that lowers the free energy. And that's exactly what it is. In an ideal solution, there's nothing energetic. Remember, all of the interactions which represent energy in an ideal solution are the same. So whether you have AA or AB or BB, all of those interactions are the same. So the only thing that can reduce the free energy per particle, or per mole, which is chemical potential at constant temperature and pressure, is going to have to be related to entropic driving force. So it's the entropy, right? All of the different arrangements that you can have that are consistent with the macroscopic constraints of temperature and pressure that are going to increase when you have this mixing, and that's what causes this decrease in the chemical potential. Okay? And hence, you will also see that once you have a decrease in the chemical potential, the total G is going to have to be lowered. Okay, so if I had just independent, let's say I had A here and I had B here, okay, we specified T, and we know we have liquid and vapor of A, we have liquid and vapor of B, okay, so this is going to have a mu A vapor at mu, and this is going to have mu B, right? But once we mix them and we have this liquid vapor system, we see that G, which is the sum of N I mu I, is going to be lowered relative to the case where we had them independently, right? So when we have this AB, this G of AB is going to be lower than G of A plus G of B, where this is now G of A and this is G of B, okay? So G is going to be less than GA plus GB, where G is the Gibbs free energy. And it all is hinging upon the fact that now the chemical potential of all species in the mixture, in this ideal mixture, are lowered relative to their chemical potentials when they were just pure. And again, we're always considering a liquid vapor system here because we're looking at this coexistence system. Okay. Any questions on that comment or comments here? Okay, so very cool, very cool. All right. So the last thing I want to address today before we go on, and I'll finish up Wednesday because it's very, very important, is that, okay, so we have now relationships with the chemical potential of mixtures, right? And as chemists in condensed phase, solid phase, vapor phase, you always have mixtures. There's not just one component, there's many components. And so we need to know what chemical potential of a particular species in the system is in order to potentially make models, or at least guide us in our experiments based on the fact that G is minimized at equilibrium, and we know that G is directly related to chemical potentials of species in the system. So if we go back and look at the expression for the chemical potential of I in an ideal liquid, so I'm just going to generalize now to a species I. It could be many species there. Okay, this could be mu I plus RT natural log x sub I. Okay, so this is a generalized form of that. You can, an I doesn't have to be 2, it can be many things. Sorry, the number of species can be many, more than 2. So this is for the ideal solution. So remember in Gen Chem, or maybe in organic chemistry, you're looking at all of these organic reactions or acid-base equilibria where everything was in the solution, right? Everything was in the solution, right? These are all aqueous systems, more or less. Okay, so there must have been some notion of chemical potentials lurking in all those discussions that you had about pH and chemical equilibria and equilibrium constants and what have you. So this is an ideal solution. How can we sort of extend the notion of a chemical potential in a non-ideal system? So how to use this expression up there as a template for writing or making a model, writing u sub I of t in a non-ideal solution. How can we use, just as we've used the ideal vapor, ideal gas models, right? We always use them as a starting point to make something more complicated, like the equations of state. How can we use the chemical potential of a species I in an ideal solution, okay, as a template for writing something for a non-ideal solution? Well, what we're going to do is just a very simple thing. What we're going to say is that mu I liquid, now for a real solution, so we'll call this real or non-ideal, is just going to be equal to what we have before, plus RT natural log x sub I, plus, and we're going to write it this way, RT natural log gamma sub I. So I'm going to introduce something called gamma sub I. This is called the activity coefficient of species I, okay, in solution. So gamma I is that's the definition. And so if I sort of, and what we see here is that this gamma I represents some departure from non-ideality. So this guy is the chemical potential of the real solution, of a species I in a real solution. We know that this guy is just the chemical potential of a species in an ideal solution, just from up here, okay? And so all we're going to do is tack on some fudge factor, if you want to call it that. In fact, you can actually derive this rigorously. For lack of time, I'm just going to introduce it to you as a fudge factor, but it is not. It's something much more deep. Okay, it's much more deep than a fudge factor. And so I'm disrespecting it, but it's okay. So we have this fudge factor that takes into account everything that is non-ideal. Okay, so just push it into gamma I. And so now we can rewrite this. Mu I liquid for a real solution is equal to mu I sat of t. So we have an RT log x plus an RT log gamma. I'm going to combine them. I'm going to go reverse. Remember earlier I split things. Now I'm going to put them back together. So this is going to be RT natural log gamma I x sub I. Okay. And we see here now that we have a very nice and compact form to think about non-ideality. If you have an ideal system, gamma I is going to equal 1, because once we let gamma I equal 1, we're going to recover this expression, which was our expression for the ideal solution. And if gamma I, if it's non-ideal solution, gamma I is not going to equal 1. It can actually be greater than 1 or less than 1, but it won't equal 1 if it's non-ideal. And so all of that non-ideality is swept into this thing called gamma I, the activity coefficient. Okay? And we can make this even more compact, and this is how you see this in the literature, and this is really the most fundamental way to think about things when it comes to chemical potential, is we're going to say that there's a thing called A sub I, which is the activity of species I. We're going to define it as gamma I times x sub I, and this is the activity of species I in a solution. Okay? This is an important concept, the activity. Now, in everything you've done since freshman year, or maybe even high school in your chemistry or physics courses, what you have assumed, and this is what no one has told you, okay, what you have assumed, and for good reason, because, well, the biggest reason is that everything works, right? You can use it, and when you apply it, it works. But it's only because of the conditions that you apply them in. What you've been assuming all this time is that gamma I is equal to 1. Whenever you talked about pH, whenever you talked about chemical equilibria, equilibrium constants, what have you up to this point, you have assumed for a good reason, that gamma I has been 1. Okay, so you've assumed everything to be ideal. Right? So in fact, in reality then, for a species I in the condensed phase, you have mu I sat, I'm almost done, I know I'm running late, plus RT natural log of A sub I. And this is the most general way to think about chemical potentials. You have some reference state, and I'm actually going to make this one step, and this is the final thing, the final thing, mu I in some reference state plus RT natural log A sub I. This, okay, is the sophisticated way of thinking about chemical potentials, and this will apply anywhere in the world, in the universe, as far as we know when it comes to thermodynamics. So the chemical potential of a species I in a mixture, whether it's gas, it's liquid, it's a solid, is going to be a chemical potential of that species in some reference state. And remember, mu is just G. We can specify what G is, right? And we can specify any reference we want, but we have to be clear, we state it, and we tell people that when we're talking to people, we have to tell them what that reference state is. So the chemical potential of I in a mixture is equal to its chemical potential in some reference state, which can be pure or a mixture, plus this thing that leads to non-ideality, that gives rise or is associated with non-ideality, A sub I. And A sub I, again, is gamma I x sub I. And when gamma I is 1, you have ideal. And when gamma I is not equal to 1, it can be greater or less than 1, it's non-ideal or real. Okay? So this is your bang for your buck in this upper level course. This is something that's going to apply anywhere, whether you're an organic chemist, physical chemist, whatever, inorganic chemist, okay? Analytical chemist. All right, so I will show you how this is applied next class, because this is so important, okay? I will do an example for the phase equilibrium that the binary stuff, one particular calculation. And I'll post the chapter for this reading. I think you might have figured it out. I think the reading has been posted. I'll assign some problems so that you can get some more practice. Okay, thanks for your attention. I ran over. Any questions before I end the meeting? Okay, have a great week. Hang in there, it's almost over. It was a great discussion. Thank you all. Have a great day.